This is the 24th physics lesson that we're going into. This is the conservation of energy. This is the lesson you want to have after you've had mechanical energy. The last lesson we learned about kinetic and potential energy. So we'll look at the difference between an open and closed system. We'll look at different forms of energy. We'll talk about what energy being conserved means. We'll be able to solve different problems in different ways. So nothing really new here. We got energy, which is in joules, kinetic potential. We're going to look at how it transfers from one to the other, and just units that we used before. These are the equations we'll talk about during this lesson today. So a system is an object or collection of objects designed. It's really defined by you. If you are studying a room, your system is everything in that room. If you're studying a house, your system is everything in the house. If your system is a universe, then you're studying everything. So it's as big as you want it to be, and everything on the outside is going to be considered the environment, also considered the surroundings. You might hear both terms being used. Open system versus closed system. The closed system is exactly what you see here. There's no transfer of energy, forces, or anything else within the system and the environment. Everything's just staying inside. Closed system, there is going to be a transfer. So you're going to lose some heat, you're going to lose some different things, we'll see. So the law of conservation of energy states, energy is neither created nor destroyed, just transformed from one form to another. And in closed, isolated systems, energy would remain constant in the system. It would go this law of conservation would pertain to the system itself. Whereas in an open system, you're going to have, it's not going to be exactly the conservation of energy, because you would have some loss, but not lost to the universe, just lost to the system itself. Different forms of energy in nature include chemical, mechanical, light, heat, nuclear, electric. And so I'm thinking about when a firecracker explodes, chemical potential energy is created, or is not created, is transformed into light, heat, and kinetic energy in a flash, in the bang, and you know, if you're close by it, you'd feel the heat as well. And so it's not lost, it's just converted. So the heat will be going out of the system, the firecracker would be moving, the light would also be kind of lost at that point in time. Not to the system, not to the universe, just to the system itself. Okay, so when we're considering the universe, energy is conserved in the universe, but not an open system. So this is going to be, most of the systems we'll have are going to have heat being lost, but we're going to pretend like we don't have heat loss. We're just going to go and we're going to study systems. We're going to pretend like we're going to look at mechanical energy mainly, and we're not going to have energy lost as heat unless I tell you that it's going to be lost as heat in the problem, and I ask you how much would be lost. Besides that, we're going to pretend like it's just going back from kinetic to potential, from potential to kinetic, and we're going to look all of mechanical energy. Mechanical energy is energy in motion, which is kinetic, or that can become motion, which is potential. So it's all the potential energy, all the kinetic energy is going to be, the term is mechanical energy. That's what this is saying right here. And we're just going to focus on the transfer of between kinetic and potential. And we're going to have initials at the beginning of the scenarios. This will be the beginning right here. And this is going to be the end over here. And so we'll be setting systems. We're looking at this, and right now, going with conservation of energy. Everything before equals everything after. So we're going to have to kind of derive. Well, you can derive an equation, or you can just start at the beginning every single time and decide how you break this equation out. I'm going to teach you how to do that. We're going to look at that in a few seconds. But any one of these things could be converted, can be substituted for this mgh initial. This could be substituted for the 1/2 mv squared initial. This could be substituted for the mgh initial. This ke could be substituted for 1/2 mv squared final. These would be finals over here at the end. And so you'll see through the example as we work through problems. Before I do anything, we're gonna go ahead and we're gonna take a look at these different problems. I'm gonna go through, before we solve them, I'm gonna show you different ways that I would deal with the different variables and how to get to a final equation that I would start plugging numbers into. So there's your conservation of energy equation. This is the one that's often drawn somewhere. It's going to be the overall, broken out completely into potentials and kinetic energies before and after. But we're going to use a mod of this equation. We might sometimes use potential energy here instead of mgh, whereas we'll keep everything else. So I'll give you tons of examples to get you to understand what I'm talking about. Mass, if we have the entire equation just like this, we don't need mass. Mass is everywhere, so we can divide up mass. When we divide up mass, here's our new equation. So that's an equation that you can write down and have if you don't have mass. So don't be freaking out if you don't have mass and you have to use this equation. It's probably a good problem still. It's probably just a problem where you don't need mass because it cancels itself out. So when you would need mass, if we ever didn't have this broken down, like if we are asked for PE there, KE there, PE there, KE there, any one of those places, well, we can't break mass out of PE because it doesn't have mass. This is an overall number. So anytime you're solving for potential energy or given potential energy or kinetic energy, solving for either of those or given either of those, you are not going to be able to divide out mass. So we'll look at this equation. We'll see how the energy is converted from that potential to all kinetic at the end. And I'll ask you about different parts in the journey, giving you information. Maybe giving you information at here, asking about information there, like what's the velocity here based on something you get up here. We are going to deal with a perfect ideal situation. Energy is not going to be lost. So mechanical energy, it's all coming from mechanical energy. Mechanical is kinetic plus potential. If you take a look, this never changes. Add this one and this one up together, the kinetic and potential at any given spot, and they're going to equal that mechanical energy because they are part of mechanical energy. So we start off with 0 kinetic, you end off with 20,000 joules of kinetic energy. You start off with 2 to 20,000 joules of potential, and you end up with 0 because it all got converted from potential to kinetic during the fall. So let's look at these examples. Here I'm giving a 50 joules of potential energy. So I'm looking at, you really always start with this equation. You start thinking about what's going on. It's dropped. What's kinetic energy? So they're asking me about this when it hits the ground. Okay, so I left these as is because these are what the questions are giving, the questions giving and adding. But it's giving me a little bit more information. This object was dropped, so I know that when it was dropped, it wasn't going anywhere. So that's going to be 0. Anything times 0 cancels itself out. I know that's going to hit the ground, and at the ground's height is 0, so that's going to cancel out too. So you could either just keep it as is and just plug in zeros in place, and you'll end up getting the zeros. You can also just think, okay, well, there's no velocity, it has no kinetic energy. There's no height, no location above the ground. It doesn't have any potential energy, so you might right off the bat just say PE equals PE initial equals KE final. Just whatever you need, but this is what's really happening. This is why there's no kinetic energy at the beginning. There's no velocity. This is why there's no potential energy at the end, because it has no height. And so this is the equation that we're going to actually start substituting into once we get to the problem. So we're going to go ahead and we're going to work this problem out after we go through all different examples. So we'll get to it in a second. This is pretty easy. I could have already done it. But here you have a rock drop from a height, and it's asking you for kinetic energy when it hits the ground. So it's giving you a height, so we need to figure this out. It's dropped, so we know that's going to be 0. It's asking you for kinetic energy, and it's telling you it hits the ground. We know that's going to be 0, but just to break it out so you can see more, it's telling you the height, so we have that information. That's right there. We know that the initial velocity is 0, so that's going to cancel this out. We know that it hits the ground, that's 0. That's going to cancel this out. They are asking you for the kinetic energy, so we don't want to break this down any further. We're going to keep that because that's what the question itself is asking you for. And we can just start plugging in values from here on out. And we will do that in the next section. Let's keep on looking at these. You have a rock drop from a height of 10 meters. What's its velocity? Okay, so it doesn't ask me or give me kinetic or potential energy, so I'm going to break this down completely. And then we're going to say we're going to figure out what we can cancel out. But first of all, since we're breaking it down completely, we don't need mass. So even though if you had mass, that's fine, keep it. If not, don't worry about it. Because mass, when we divide everything out by mass cancels out, so we get this equation. So we'll start this from here, but we'll even get it even shrunk shorter because it starts with it's dropped at the beginning. It's dropped at the beginning right here. 0 velocity is going to cancel out. It hits the ground. So there's no height when it hits the ground. That's going to cancel out. So this is the equation we really will be using when we plug in values once we break this all down. You're falling at, a rock's falling at 6 meters per second at 35 meters off the ground. What's the velocity when? So this one's also going to be broken down. We're going to divide out the mass, and then we're going to figure out what else we can. So we do have a height right there, 35 meters. We do have a velocity, 6 meters per second. It hits the ground, so this can cancel out. So that's going to cancel out, so we would start with that right here. Next type of problem. You have a rock that's falling. It's 35 meters off the ground. It's asking you what is the velocity when it's 5 meters off the ground. So this is what we're going to write down, and we're not going to cancel anything out. There's nothing we can cancel out. It's not on the ground. It started falling at the beginning of this problem. It was already falling with a velocity, so we didn't cancel that first part out either. So nothing can cancel out. This one, falling 6 meters per second, 35 meters off the ground, how much kinetic energy does it have the moment it hits the ground? So we have to break that down because we are given a height, we're given a velocity. It's asking you for kinetic energy, so we're not going to break that down anymore. It's going to hit the ground, so we're going to cancel that part out. And once again, you can just realize, if you know it's off the ground, this is 0, this equation is going to start right here. This is where we're going to go with that. How much potential energy does a 1.5 kilogram rock have when dropped if it's going 26 meters per second, 5 meters off the ground? Okay, so it's asking you potential energy when dropped. That's going to be a key. It's telling you it's not on the ground and it's going at velocity at that point. So how much potential energy you have when dropped, since it's dropped, the velocity is going to be 0 initially. It is going to have a height right there at 5 meters, and it's going to have a velocity right there at 26 meters. So since that's 0, we cancel that out, and this is where we would start this equation. How much mechanical energy? So I'm actually going to go backwards. I'm going to go ahead and not even go to kinetic and potential. I'm just going to keep mechanical initially. I am going to break down this one because it's saying what's the ME at the beginning when dropped if it's going. So it's telling me information. So I'm going to break these down even further. It's giving me a height. It's giving me a velocity when it hits the ground. So this is where I would start this problem. And then this problem, I would start here. It gives me joules of kinetic energy. It gives me joules of potential energy a few seconds later. And whatever that was at the end is conserved and going to be equal to what it was with the mechanical energy, which is made up of potential and kinetic, was at the beginning. Okay, so let's go and solve the problems. So I told you how we worked through this earlier. We got to this point and we would just plug in. We have 50 joules of potential energy when dropped, and that is going to equal the joules of kinetic energy at the end. So that's what this question told you, and this is the end result. Everything converted from potential to kinetic during the fall. Rock is dropped from a height of 10 meters with kinetic energy, so we have initial height, we got that. We got this equation down here because of the zeros that we had for the beginning and the end for the velocity and the height, and then we just plug in the values from there. We have a height, we have a mass, we have an acceleration due to gravity, we have a height. And once we solve for what the potential energy was initially, we know that's all going to be kinetic energy, which is what the question is asking you for at the end. It's going to be 150 joules. So this one right here, we broke it down. We knew it started from rest. It landed on the ground. We had this equation. We could start plugging in our values, and we knew that it had an acceleration due to gravity of 10. We knew it was 10 meters off the ground, and we had everything we need to solve for a final velocity. When you rearrange this, what you're going to do is you have to multiply out 2 from both sides. That gets rid of this. You have to take the square root of both sides to get rid of that, and you end up getting this right here. And your answer there is going to be 14.14 meters per second. In this problem, we went ahead and we realized the height was 0, so we canceled out that part. We had everything else in it. And we start plugging our numbers. Acceleration due to gravity, the height initially was 35, the velocity at the beginning was 6, and we're asked for the velocity when it hits the ground. So when we do this math, we're going to go ahead and we're going to multiply all this by 2, multiply this by 2 to get rid of that, and then we're going to take the square root of everything. And so when you do all that, I went ahead and just did some of the numbers. I got 38 over here, and then I multiplied out the 2 from both sides to get rid of this thing, and I took the square root of that. And so I got 27.13 meters per second for my answer. This one right here, we went ahead and we started off with nothing we can cancel out. It was traveling at velocity, it was traveling given a height. And so when we did the math, I went ahead and put these two numbers together, I got that. Put these two numbers together, I got that. And now I went ahead and subtracted the 50 from both sides because it's added on both sides. So we can't add 50 to 1/2. This is multiplied by the v squared, v final squared. We subtracted both sides by 50, we got that, and now we can go ahead and multiply out the 2 to get rid of this. And then we can take the square root of both sides to get rid of the squared right there. And so that's what we get. We get 25.22 meters per second. Okay, so we have our initial equation, but we're not going to break out the kinetic energy because they asked for that at the end. There's no height at the end, so that's going to cancel out the height here. So we have this, we're going to plug in some numbers, and when you plug in all the numbers, you have your mass, your gravity times the height. Can't get rid of the masses because we are asked for kinetic energy. We're not asked for height or velocity. So couldn't get rid of that, and we end up getting 552 joules. If you're not getting that answer, always double check. Make sure you're squaring everything and just look at your numbers you're using. Make sure you're writing on everything on a piece of paper. How much potential energy does 1.5 kilogram rock have? So initially it's dropped. It's going to, they ask you potential energy, so we're not going to break away from potential energy. We're going to keep that initially because it says at the beginning how much does it have. It gives you everything else to plug in your numbers. When you plug in your numbers, you get 582 joules of energy. So here's asking you for mechanical energy, so we go back even one more step to keep this all as mechanical energy. We don't break it into kinetic and potential, but we have to break this down all the way to what makes up the potential and the kinetic energy. So we plug in our numbers, and when you get your answer, it's going to be 582 joules. For this one, we're not really breaking anything out because they are giving you the potential and kinetic energy a little bit later, and they're asking you for how much total initial mechanical energy, and ME is nothing more than P and KE. So even though it was dropped, this mechanical energy would have been all potential energy at the beginning. But it's asking for mechanical energy, so it doesn't matter that this is all potential because it still is mechanical energy. It just happened to be that there would be 0 kinetic at that time. So the answer here for either, if the question asks what's the mechanical energy to start off with, it's 35.7. So the question asks what potential energy you had to start off with, it would be 35.72 because it wouldn't be kinetic, and then none of that mechanical would have been kinetic. Okay, so if you have a problem that asks you about heat, you're just going to have heat would be lost. You'd have all the mechanical at the beginning, and heat would be lost during the fall, and so you still wouldn't lose it totally. You would still have it. It would just probably be losing it from the system going into the environment. So here's a question: if you had 45 joules of potential energy when dropped and 43 joules of kinetic energy when it hit the ground, so at that point in time when it hit the ground, it had no, I should have broken this down a little bit further, but it had this ME final could have been broken into potential and kinetic, and since it hit the ground, it would have had no potential energy at this point. It would have had all kinetic, and that all kinetic was 43, so it would have had 43 joules of kinetic energy, 0 joules of potential energy. That means everything else must have been lost as heat, and so heat would have been 2 joules of energy. So make sure you do this problem set before you check your answers. I'm just going to go directly to the answers and just show you the work so you can take a look at the work too if you're checking your answers. If you drop an object, does the following increase, decrease, stay the same? In an ideal situation, so a perfect situation, kinetic energy is going to increase, potential energy is going to decrease as it becomes kinetic. Mechanical energy is going to stay the same because it's an ideal situation, it's not losing it as heat. If it wasn't ideal, it would have been lost as heat. So next question, they give you that starting from rest, it's just dropped, it's hitting the ground. And when you get your answer, you're going to get 42 joules of energy. This problem, starting from rest, it's hitting the ground, but they're not asking you for, like the last one, they asked you for kinetic energy, so you didn't break that down. But they are asking you for velocity, so you're going to break that kinetic energy part final down into a little further, and we're going to get an answer of 8.37 meters per second. For this one right here, they are giving you, they're not asking for potential kinetic anywhere, so we can break it all the way down. We can divide out our masses, and we can get this equation. We can break it down even further because initial velocity was 0. Then we start plugging in numbers. When you plug in numbers, you have to subtract this 10 times 5 from this side over here. You have to subtract it from both sides before you can deal with 1/2. So if you're having any trouble getting with the algebra down, after you get this part, you multiply both sides by 2, and then you can take the square root to get rid of the VF squared. So you'll end up getting this answer right here, 11.83 meters per second. This problem, it starts from rest. They are asking you for the final kinetic energy, so you can't break that down. You can break everything else down. You can get rid of the initial velocity being 0. You can get rid of the initial kinetic energy because that's 0. And so we have all our numbers we can plug in. Solving for kinetic energy, you get 245 joules. This problem, roller coaster is going down the track. It has a velocity, it has a height, so it has a potential and kinetic energy. And they're asking you for a final velocity. So we can break it all the way down. We're given initial height, we're given initial velocity, we're given a final height, and we're asked for the final velocity. We have everything we need to do to solve this. Make sure you add these two together and then subtract this number from both sides. And then you multiply out the 2, and I think I did some of that for you. And once you multiply out the 2 and take the square root of the final answer, you get 27.49 meters per second. Here you have a pool ball. It's flung off table. It's going to hit the ground. So it is asking you for a velocity at the end. So you're not going to. It's not giving you any potential kinetic energy. So we're having the whole equation, but we get to the good thing is we get to divide out the mass and not even worry about the 0.16 kilogram pool ball. And so we just plug in numbers from here. Take that. We're going to subtract both sides by this right here. And when we subtract both sides, we end up getting this number right here. So you take this, once you're done with that, and you subtract this over here from the other side from it, you should get 17.91, and then we're ready to multiply it by 2 and take the square root of it to final it out, and we get 5.98 meters per second. Okay, we have a pool ball. It's flung. We're asked for mechanical energy when it hits the ground. It is moving with it is off the ground. It is moving at the beginning. It is off the ground at the beginning, and so we're going to break these down as far as we can go as your potential energy and your kinetic energy. So we can plug in the numbers to that, and once we solve for all of this initial potential and kinetic energy, we're going to know mechanical energy at the end, final, because it's going to come from all the mechanical energy or the potential plus the kinetic at the beginning. And so when we get that answer, it's going to be 12.77 joules. And we would have started off with 12.77 joules, and we ended up with 12.77 joules. That's why we could do this equation right here.